the 15th of August, 1977. A quiet night at Ohio State University's Big Sur radio telescope. Then suddenly, a burst. A narrowband signal so sharp, so clean, it slices through the static like a blade. For exactly 72 seconds, the universe seems to whisper in perfect mathematical precision. 1,420 megahertzes, the hydrogen line, the frequency of the most abundant element in the cosmos, and perhaps the one any distant intelligence would choose to speak with. Astronomer Jerry Eman circles the printout, scrawling one word in the margin: wow. It becomes the most famous exclamation in the history of radio astronomy. And then, silence. No repeat, no source. Just that one impossible moment suspended in data, unresolved for nearly half a century. Fast forward to the 3rd of October 2025. Over Mars, the ExoMars Trace Gas Orbiter catches a flicker, a streak of light flashing across the planet's upper sky at nearly 210,000 kilometers per hour. ESA's team releases the footage a few days later, a bright dot racing through the thin Martian atmosphere, gone in seconds, leaving behind more questions than answers. The object? An interstellar visitor named 3I Atlas, on course for its perihelion near the end of the month. And somewhere, deep in the static of the cosmos, a familiar frequency hums once more, 1,420 megahertz, the same spectral fingerprint as the wow signal. Coincidence? Echo? Or the first hint of a connection spanning 48 years and hundreds of millions of kilometers? Tonight, we embark on a new journey, where the theme of 3I Atlas, the 1,977 wow signal, could it be the same object, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you listening from tonight? Tell me what the sky looks like where you are. It's always fascinating to see who's joining us from all around the world. So, here's where our story begins again, with a faint flash above Mars, a signal long gone, and the thin, invisible thread that may connect them traced through light, dust, and a single frequency at 1,420 megahertzes. The vast, silent ocean of space is not truly silent. It is filled with the faint, persistent whisper of hydrogen, the universe's most fundamental element. This whisper resonates at a specific frequency, 1,420 megahertz, the hydrogen line. It is a natural beacon, a radio fingerprint that any technological civilization would recognize. And it was upon this precise frequency that the now famous wow. The signal was detected in August 1977, a sharp, powerful burst that appeared to be everything we might expect from an artificial interstellar message. For decades, the dominant hypothesis has been one of intelligent origin, a fleeting call from the cosmos. But what if we have been misinterpreting the universe's handwriting? What if the wow signal was not a crafted message, but the signature of a natural cosmic laser, a maser powered by hydrogen and ignited by a passing stranger? The standard interpretation of the wow signal rests upon its remarkable conformity to predicted interstellar communication parameters. It was a narrowband signal, concentrated around the hydrogen line, a logical choice for any civilization seeking to announce its presence. It was intense, far exceeding the background noise, and it lasted for 72 seconds, the approximate duration for which the Big Sur radio telescope's fixed receiver could observe a single point in the sky as the Earth rotated. According to current models of technosignature searches, the signal's profile is a near-perfect match for an artificial beacon. Scientists suggest this could be due to a powerful directional transmission aimed fortuitously in our direction, The signal's brevity and failure to reappear are attributed to the transmitter ceasing or simply being pointed elsewhere. It is a clean, logical, and profoundly compelling explanation. Yet, that very cleanliness is its greatest weakness. It is a hypothesis that exists in a vacuum, a single data point of perfection in a messy, dynamic universe. If it was a beacon, why has nothing like it ever been heard again, despite decades of dedicated searching? The silence that followed is as deafening as the signal itself. A new speculative hypothesis is now emerging from the confluence of a revolutionary discovery and a re-examination of old data. The key may lie not with a distant civilization, but with our first known interstellar visitor, the object designated 1I Oumuamua, and its kin, such as the comet 3I Atlas. These wanderers from other star systems are natural probes, sampling the galactic environment in ways we are only beginning to comprehend. Recent analyses from 2024 and 2025 of archival data, around 1420.726 MHz, have revealed intriguing narrowband transients recorded near known hydrogen clouds. Could the WOW signal have been a similar, albeit far more powerful phenomenon? The hypothesis is that an object like 3I Atlas, traveling at immense speeds through a dense, neutral hydrogen cloud in the constellation Sagittarius, could have acted as a catalyst. The interstellar medium is not uniform. It is a tapestry of filaments, clouds, and voids. Data from the LAB and HI4PI all-sky hydrogen surveys confirm that the region from which the WOW signal originated is particularly rich in these dense HI structures. As an interstellar object plows through such a region, it does not pass quietly. At the first level of this hypothesis, the explanation is elegantly simple. Imagine 3I Atlas as a swift-moving projectile. As it traverses a particularly dense, localized pocket of hydrogen gas, the resulting shockwave and turbulence could briefly energize the atoms, causing them to emit stimulated radiation, a natural maser, at the 21-centimeter line. This burst would be intense, localized, and transient, lasting only for the duration of the object's passage through the pocket. It would appear, peak, and vanish, much like the WOW signal itself. This scenario requires no unknown physics, only a fortunate alignment of a dense hydrogen cloud and a high-velocity intruder. It is a cosmic coincidence of the highest order, but one that the vast scale of the galaxy makes statistically plausible. Is it possible that we have spent half a century searching for a builder, when we should have been looking for a spark? But what if the mechanism is not merely a passive interaction, but an active, cyclical process inherent to the interstellar object itself? This second level of hypothesis proposes a more dynamic actor. We know that solar system comets undergo outgassing, releasing jets of vapor and dust as they are warmed by the sunday. While an interstellar object in the depths of space is far from any star, it may not be entirely inert. Internal heat from residual radionuclides, or the slow release of trapped volatile gases from its interior, could lead to sporadic, low-level outgassing. If 3I Atlas possessed such a mechanism, its journey through a hydrogen cloud would be profoundly different. The expelled gas from the object would act as a piston, compressing the surrounding neutral hydrogen ahead of it. This sudden, intense compression could amplify the natural maser effect by orders of magnitude, creating a brilliant, repeating flare of 1420 MHz emission each time an outgassing event occurred. This would no longer be a single coincidental flash, but a predictable, though rare, symphony of light. Could the WOW signal have been just one fortissimo note in a sporadic, interstellar composition, its repetitions lost in the noise, or simply yet to be observed again? The third, and most profound, level of speculation ventures into the realm of cosmic architecture. It posits that an object like 3I Atlas is not merely a rock or a block of ice, but a component in a vast, natural amplifier. Its unique surface chemistry, perhaps a crystalline water-ice matrix forged in an alien stellar system, could act as a catalyst or a resonant structure. Furthermore, the long trailing coma of dust and plasma, the object's atmosphere, could interact with the interstellar medium to form a complex, geometric cavity. This structure, a natural analogue to a man-made laser's resonant chamber, would be shaped by magnetic fields and plasma dynamics. Under the right conditions, as the object moves through a gradient of hydrogen density or a region of particular magnetic alignment, this entire system could momentarily achieve coherence. The result would be a burst of radio energy so focused and so powerful that it mimics an artificial signal with uncanny precision. The wow! The signal would then be the output of a natural, interstellar musical instrument, played by the random motions of the galaxy. Are we, in our search for complexity, failing to appreciate the intricate and unexpected symphonies that nature itself can compose? If this natural Masa hypothesis holds any weight, its implications are transformative. It would resolve the 48-year mystery of the wow signal, not by diminishing its wonder, but by recontextualizing it within a new, dynamic astrophysics. We would have a new tool for galactic cartography, using these rare, powerful bursts to map the densest and most turbulent, high nozzles and shock fronts within our galaxy. The search for extraterrestrial intelligence would gain a new filter, a way to distinguish potential false positives from true technosignatures by analyzing the signal's substructure and context for the hallmarks of natural amplification. Most importantly, it would force us to see interstellar objects not as inert fossils, but as active participants in the interstellar medium, capable of illuminating the hidden structures of our galaxy in spectacular, if fleeting, ways. But to move from speculation to evidence, one critical foundational question must be answered, a question that has lingered for nearly half a century. Could an object like 3I Atlas have even been in the right place at the right time to create such a phenomenon? The answer lies not in the radio static of the past, but in the precise celestial mechanics of the present. Tracing a path backwards through time to see if the trajectories of our interstellar visitors could ever intersect with the origin point of that famous signal. The 48-year puzzle remains. Does the kinematics even allow for a coincidence of such cosmic proportions? For 48 years, the enigmatic wow, the signal has stood as a solitary monument in the desert of our cosmic silence, a brief, brilliant flare in the hydrogen line that has never repeated. It is a temporal artifact, a moment frozen in the late summer of 1977, its origin a set of celestial coordinates now etched into the annals of astronomical mystery. The recent arrival of the interstellar object 3I Atlas, a wanderer from the depths beyond our sun's influence, presents a profound and tantalizing question. Could these two disparate events, separated by nearly half a century, be connected? Is it dynamically feasible for the trajectory of 3I Atlas to be traced backward, through the complex gravitational choreography of the inner solar system, to intersect the very patch of sky from which the wow signal emanated? Orbital mechanics, a discipline of pure mathematics and unyielding physical law, holds the only key to this temporal lock. The equations do not care for our mysteries, they simply are. They will provide a calm, calculated answer, revealing whether a path exists that connects the here and now of 2025 to the there and then of 1977. The conventional approach to such a problem is one of meticulous reconstruction. Using advanced celestial dynamics software like Rebound and the highly precise ephemerides from JPL Horizons, astronomers would begin the painstaking work of reverse engineering the object's path. They would account for every gravitational perturbation, from the dominant pull of the Sun to the subtle tugs of the planets, and even incorporate the faint but persistent pressure of the solar wind. The goal is to refine the orbital elements of 3I Atlas with the data from its 2025 apparition, then run the cosmic clock backward to see if its path, within a defined margin of error, passes through the refined right ascension and declination of the WOW signal. This is the established methodology, a testament to our sophisticated understanding of motion on a solar system scale. Yet, one must wonder if our models of the solar system's gravitational field are refined enough to trace a perfect path across 5 decades, or if unknown micro-influences lurk in the void, subtly altering the course of such a small, fast-moving body. What if, however, the journey of 3I Atlas was not a solitary voyage through empty space, but a guided one? A more speculative hypothesis suggests this object may not have been subject solely to the chaotic interplay of gravitational forces. Perhaps it travelled along a pre-existing pathway, a gravitational rail, formed by the subtle density waves of the galactic tide, or even within a vast unseen interstellar magnetic tube. Such structures, theorized by some models of galactic dynamics, could act as channels, funneling material across the immense distances between stars and constraining their possible trajectories to a limited set of corridors. This would reduce the element of chance, making a connection between 2 specific points in space and time less a matter of random chance and more a consequence of a larger, underlying cosmic architecture. Could an object's path be so predetermined, its origin and destination so intrinsically linked by the fabric of the galaxy itself? The analysis of this celestial backtracking yields 3 distinct possibilities, each with its own profound implications. The first level is one of simple, stark negation. The reverse integrated trajectory shows no intersection with the WOW signal region. In this scenario, the compelling narrative of a connection dissolves. The hypothesis that 3I Atlas was the source of the 1977 signal is significantly weakened, forcing a shift in focus. The search would then turn toward more conventional explanations, such as a natural astrophysical maser, a cosmic laser within the interstellar medium that briefly flared and then fell silent. But does the failure of one beautiful hypothesis truly invalidate the strangeness of the object itself, or merely redirect our search for understanding? The second level presents a more tantalizing edge-of-knowledge result. The calculated path intersects the WOW error box at its very boundary. This is the liminal space, where the precise initial conditions and the fidelity of our models become paramount. The margin of error is both a curse and a blessing. It keeps the possibility alive, if only just. It opens a narrow door, one that demands more data to determine if it leads to a revelation or a dead end. The close Martian encounter in early October 2025, observed by the ExoMars Trace Gas Orbiter, provides that crucial new data point, a precise positional fix that allows for a final, refined orbital calculation. The universe, it seems, has offered us one more chance to measure, to know. But will this final piece of the puzzle bring clarity, or simply deepen the ambiguity? The third level is the most staggering, a deep, unambiguous intersection. The retrograde orbit of 3I Atlas, with a high degree of confidence, places it within the heart of the WOW signal's origin point in 1977. This is no longer mere coincidence. It is a story written in the language of motion. It suggests that as this interstellar traveller sped through our outer solar system 48 years ago, it interacted with a cloud of neutral hydrogen in a way that produced that singular, powerful burst that it plucked the hydrogen line string, creating a resonant note that briefly captured our attention. The implications of such a confirmation would be monumental, transforming 3I Atlas from a simple interstellar rock into a historical artifact of the first order. What other secrets might its composition hold, if it were indeed the source of one of the greatest modern astronomical mysteries? Should the orbital mechanics permit this connection, the astronomical community would mobilize as never before. A multi-wavelength campaign would be launched, a global effort to scrutinize the object as it reaches perihelion, searching for any sign of activity, any repeat emission, any outgassing pattern, any chemical signature that could serve as a confirming fingerprint. The hope would be to catch it in the act once more, to witness a recurrence and finally validate the link. But if the trajectories remain separate, the lesson is equally valuable. It reveals the current limits of our ability to trace the origins of these faint, fast interstellar visitors, reminding us that their vague and distant origins place their past motions largely beyond our definitive reconstruction. So, we are left with a single, pivotal question, the answer to which lies in the precise orbital data soon to be delivered from the vicinity of the red planet. What new truths will be unveiled when the precise trajectory of 3I Atlas, as it swung past Mars, is finally revealed to the waiting world? On the 3rd of October, 2025, as the interstellar visitor designated 3I, Atlas made its close approach to the red planet. The ExoMars Trace Gas Orbiter turned its instruments towards the void. From its unique vantage point in Martian orbit, the object was not a point of light in a terrestrial telescope, but a swift, silent streak against the ochre plains below a precise, orbital measurement of a traveler from another star. The data it captured was a simple sequence of positional fixes, a fundamental act of celestial cartography. According to current models, this was a routine tracking exercise, a crucial data point to refine the object's trajectory before its final, fiery plunge towards the Sunday. The velocity, calculated at approximately 210,000 km per hour, was consistent with the hyperbolic path expected of an interstellar comet. Yet, in that brief transit, was the orbiter merely a passive witness to a predictable astronomical event, or did it capture the first, a subtle hint of an anomaly that would challenge our very understanding of such visitors? The European Space Agency's subsequent release of a data visualization, a GIF depicting a faint dot racing across the Martian sky, provided the global astronomical community with an unprecedented constraint. For the first time, the path of an interstellar object was triangulated from a platform beyond Earth, a feat of interplanetary surveying that eliminated the parallax and atmospheric distortions inherent in ground-based observations. This data, spanning from the 7th to the 12th of October, became the new gold standard, allowing professional and amateur optical groups alike to calibrate their light curves with exquisite precision. The orbital elements were refined with a new level of confidence, seemingly closing the case on the object's natural origins. But does a more perfect measurement of a trajectory necessarily lead to a more perfect understanding of the traveler itself? Or does it merely sharpen the outline of a mystery we have yet to fully define? The initial, mainstream interpretation of the TGO data was one of pure orbital mechanics. The object was a natural body, a shard of ice and rock from a distant stellar nursery, and its flyby of Mars was a gravitational perturbation to be calculated, not a phenomenon to be questioned. The faint streak of light was simply sunlight reflecting off a dormant nucleus. This is the foundation upon which all conventional comet science is built. Yet, a more speculative hypothesis proposes that the Martian environment itself may have acted as a catalyst. The tenuous but dynamic plasma field that envelops Mars, a relic of its lost magnetic field, could have interacted with the comet's own nascent coma. Could this plasma sheath have momentarily energized the dust and ice particles being shed from 3I Atlas, inducing a transient, glowing tail visible only from the privileged perspective of orbit? The data shows a brief, anomalous brightening that the pure reflection model struggles to fully account for. If not a trick of the light, then what unseen force briefly ignited this visitor's engine? This leads us to the first level of deeper analysis. The data merely improves the orbit, a testament to natural, predictable mechanics. This is the null hypothesis, the bedrock of scientific skepticism. Yet, the second level acknowledges a short-term variation in luminosity, a flicker embedded within the light curve. Scientists suggest this could be due to a minor outburst of gas, a pocket of volatile carbon monoxide or carbon dioxide. Ice sublimating suddenly under the sun's heat, a common, if unpredictable, behavior in solar system comets. But that does not account for the specific timing and the unique electromagnetic environment the object was transiting. What if the outburst was not entirely self-generated? The third, and most provocative, level of analysis introduces a correlation that stretches the boundaries of coincidence. During the same narrow window of the TGO observation, deep space monitoring networks recorded a transient, anomalous burst in the 21-centimeter hydrogen line, a fundamental frequency of the universe. The mainstream explanation would point to a natural maser effect, perhaps amplified by the interaction of the solar wind with an interstellar cloud. However, the synchronicity with 3I Atlas's Martian passage is a bold and tantalizing suggestion. Could the object itself have been the source, its brief plasma-induced activity stimulating a coherent microwave emission from the hydrogen in its own coma or in the local interstellar medium? This is a hypothesis that ventures from natural physics into a realm of profound implication. Is it possible we witnessed not just a comet, but a complex natural amplifier, or perhaps something more? The consequence of this extraterrestrial observation is a paradigm shift in how we will study future interstellar guests. We have now entered the era of interplanetary triangulation, a method that will systematically remove the terrestrial bias that has always colored our data. By observing from Mars, from future orbiters at Venus, or from spacecraft in the asteroid belt, we can construct a three-dimensional understanding of these objects' trajectories, compositions, and behaviors with a fidelity once thought impossible. This disciplined, multi-perspective approach is not just about understanding their origins, but is fundamentally about the disciplined search for techno-signatures, eliminating the noise of our own planet to listen more clearly to the signal of another. If an object were to exhibit even the subtlest of non-gravitational accelerations or anomalous emissions, this new network would be our most sensitive instrument for its detection. So, as we refined the path of 3I Atlas from another world, we were not just charting a course, we were laying the groundwork for a new type of inquiry, one that asks not only where an object comes from, but what it truly is. And, as the refined orbital data pointed telescopes back towards the approaching visitor, what new secrets would its evolving form reveal when viewed from the clearer skies of Earth orbit? On the 21st of July, 2025, the Hubble Space Telescope turned its gaze toward an object designated 3I Atlas, an interstellar visitor on a trajectory through our solar system. What it captured was not the diffuse, spherical cloud of gas and dust typical of a comet's coma, but a distinct, asymmetric form, a teardrop. This single, elegant geometry, frozen in the void, tells a story written in the language of solar wind and outgassing. According to current models of cometary science, such a shape is a direct consequence of the relentless pressure exerted by the solar wind, sculpting the volatile material sublimating from the nucleus into a streamlined form, a cosmic weather vane pointing directly away from our Sunday. The ice and dust within the object are behaving as one would expect, reacting to the external forces of our star. But does this conventional explanation fully account for the precise, almost aerodynamic contour of this particular teardrop, or does its very perfection hint at a more complex internal architecture? The mainstream interpretation suggests that the teardrop morphology is a classic indicator of an active icy body. The force of sunlight heats one side of the nucleus, causing ices to turn directly into gas, which carries dust with it to form the coma. The solar wind and radiation pressure then push this material away, creating the tail and shaping the coma. For 3I Atlas, this process appears to be highly anisotropic, with outgassing occurring not uniformly, but from specific, localized regions on the surface. This is not unprecedented. Many comets exhibit jet-like features, yet the sharp definition and sustained asymmetry of this teardrop coma are remarkable. It presents not as a chaotic puff of vapor, but as a structured plume. Could such a consistent form be maintained by a simple, tumbling ice ball, or does it require a more stable and deliberate source of emission? This leads us to a more speculative hypothesis. Imagine that the surface of 3I Atlas is not a homogeneous mix of ice and rock, but is instead crisscrossed by a network of fissures and vents. These would not be random cracks, but a coordinated system of apertures. Under the increasing heat of the sun, these vents could open not in a chaotic sequence, but in a synchronized fashion, transforming the object from a simple outgassing body into a multi-jet nozzle with a distinct rhythm. The resulting teardrop would then be the product of this precise internal engineering, a controlled exhaust rather than a passive evaporation. Is the shape we observe merely a product of solar sculpting, or is it the visible signature of a complex, active surface, a system of synchronized jets that operates with a purpose we have yet to discern? The data and evidence, published on the 7th of August, 2025, provide a foundation for this inquiry. At a distance of approximately 277 million miles, Hubble's resolution was pushed to its limits, yet it yielded critical information. The morphology of the coma and its skewed tail strongly suggest a nucleus rich in volatile ices and active dust. Reflectance, spectroscopy, and analysis of the dust grain structure are the primary tools for distinguishing a natural comet from something born of a more speculative, technological origin. The initial spectral data indicate the presence of silicates and water ice, constituents common to countless comets within our own solar system. This aligns perfectly with a natural explanation. But what if the key lies not in the composition of the material, but in the pattern of its release? A pattern that current spectroscopy is not designed to detect. Our analysis and inferences must therefore proceed through escalating levels of complexity, each building upon the last, each pushing the boundaries of the plausible. At the first level, we confront the asymmetric coma. The mainstream scientific explanation attributes this to the object's slow rotation. As the nucleus spins, different regions are exposed to solar heating, leading to uneven outgassing. A single, particularly active jet on the sunward-facing side could easily produce the teardrop shape, its direction shifting slightly with the object's rotation in a predictable Keplerian dance. This is the simplest and most elegant solution, requiring no new physics, only the application of well-understood principles to a new interstellar object. Yet, if the rotation were the sole architect of this form, would we not expect to see a greater wobble in the coma's orientation over time? A slight wavering in the pointing of the teardrop as the jet source moves in and out of sunlight? Progressing to the second level of analysis, we must consider the possibility of cyclical jets. Hubble's initial image is a snapshot, a single moment in the life of this object. Subsequent observations, however, may reveal that the outgassing is not constant but pulsed. These periodic bursts could be the result of complex thermal cracking deep within the nucleus, a natural geyser-like effect. But what if this periodicity is so regular that it transcends simple geology? Such rhythmic, repeating puffs from a coordinated nozzle system could produce not only the stable teardrop, but also synchronized optical brightening. And if these jets are composed of charged particles, their cyclical nature could, in theory, generate a low-frequency radio emission in phase with the optical flashes. The object could be pulsing across the electromagnetic spectrum, a lighthouse whose signal we have only just begun to notice. Are we observing a natural, if complex, cryovolcanic process, or are we witnessing a form of modulation, a carrier wave encoded in dust and gas? This brings us to the third and most profound level of inference: resonant geometry with the interstellar medium. The hydrogen line, the 21 centimeter emission from neutral hydrogen atoms that permeates the galaxy, is the background hum of the universe. It is a constant, a baseline. The speculative hypothesis proposes that the specific, teardrop-shaped cavity being carved out by the synchronized jets of 3I Atlas is not a random shape. Its geometry, the precise contours of its ionized boundary, might be unintentionally or intentionally designed to act as a resonant cavity. As the object moves through the interstellar medium, this cavity could be amplifying the ambient 21 centimeter radiation, much like a musical instrument's body amplifies the vibrations of a string. The teardrop would become a natural maser, focusing and strengthening this universal signal into a narrow, powerful beam. Is it possible that we are not looking at a comet, but at a self-propelling antenna, its form and function merged into a single, elegant system for communication or propulsion? A system that uses the very fabric of space as its medium. The implications of this are as profound as they are selective. Each Hubble image of 3I Atlas is more than a photograph. It is a mold from which we can cast a model of its surface activity. By understanding the pattern of its jets, by mapping the rhythm of its outgassing, we can create a predictive timetable. This model would tell us not just how the object behaves, but when it might be most active in a specific, resonant way. It would allow us to forecast the moments of peak emission, to predict when, and crucially, where in the sky we should point our most sensitive 21 centimeter radio telescopes. We would no longer be listening at random, we would be waiting for a predicted signal, aiming our antennas at a specific point in space and time, hoping to catch not static, but a structured message. Could this meticulous analysis of a dusty teardrop ultimately provide the coordinates and the timing to capture a modern-day equivalent of the legendary "wow" signal? A signal not of chance, but of calculated prediction. The trajectory of this enigmatic object now becomes the critical factor, the clockwork that will drive its future activity. As it continues its journey inward, the solar heating will intensify, potentially activating more of its hypothesized nozzle network. According to NASA's overview, last updated on the 2nd of October, 2025, 3I Atlas poses no threat to Earth, with its closest approach remaining a safe 1.8 astronomical units away. Its path is set, its destiny governed by gravity. It will reach its perihelion, its closest approach to the Sun, on or about the 30th of October, 2025, venturing just inside the orbit of Mars at a distance of approximately 1.4 astronomical units. This pivotal moment, this brush with the fires of our star, will be the ultimate test of its nature. Will the increasing solar energy cause it to erupt in a spectacular, yet ultimately natural, display of cometary fury, or will it trigger a more refined and precise response, activating a system whose true function has until now remained dormant? The parameters of its journey are now known, but the outcome of its close encounter remains one of the solar system's most compelling and open questions. The cosmic calendar has been set. On or around October the 30th, 2025, the interstellar object designated 3I Atlas will plunge through its perihelion, its closest approach to our Sun, at a distance of approximately 1.4 astronomical units. This is not merely a celestial event, it is a stage, perfectly set for a series of profound tests. The object's trajectory, threading the space between the orbits of Earth and Mars, places it in an ideal position for observation, a silent visitor from the abyss, now moving into the spotlight of our star. According to current models, this increase in solar energy should trigger a predictable surge in outgassing, a brilliant but silent eruption of dust and vapor. The ice, slumbering for eons in the deep freeze of interstellar space, will awaken under the solar glare. But what if this awakening is not merely a physical process but a functional one? What if, as it nears the furnace of our star, the comet's nucleus stirs with such intensity that its ion tail transforms into something far more complex, a vast, naturally forming plasma antenna tuned to broadcast on a universal frequency. The latest data, updated as of October 2nd, 2025, provides the framework for this encounter. NASA's comprehensive analysis confirms the object poses no threat to Earth, its closest approach remaining a safe 1.8 astronomical units away, its orbit carrying it safely interior to that of Mars. Forecasts predict a significant increase in brightness as solar heating intensifies, a direct consequence of the sublimation of ices. This is the conventional narrative, the one grounded in the well-understood mechanics of cometary physics. We expect a coma to form, a tail to stream away, a spectacle of reflected light. Yet, this very predictability is what makes the upcoming perihelion the perfect laboratory. For if there is a deviation from this script, even the slightest anomaly, it would stand out with stark clarity against the backdrop of expected behavior. Could it be that we have been misinterpreting the nature of these interstellar travelers all along, seeing only inert rock and ice, where a more intricate mechanism lies dormant? Let us then embark on a structured analysis, a hierarchy of possibilities that escalates from the conventional to the profoundly speculative. At the first level, we have the linear increase in activity. The comet brightens precisely as predicted, a beautiful, pristine point of light in our telescopes. Its radio signature remains, a silent hiss of thermal emission, the expected radio-quiet nature of a simple mixture of water, carbon monoxide, and dust venting into the vacuum. This outcome would be a success for conventional astronomy, confirming our understanding of cosmic chemistry. Yet, it would also be a quiet disappointment for those who peer into the darkness and wonder if we are truly alone. For if this object is just another rock, however distant its origin, then the profound silence of the universe remains unbroken. But what if the silence does not hold? The second level of our analysis introduces a more tantalizing prospect: short, powerful bursts of radio emission. As the comet's activity reaches its peak, the proposed plasma antenna, the structured magnetized ion tail, becomes a reality. Within this turbulent stream of charged particles, natural maser action could amplify faint signals into powerful coherent bursts. And the most compelling frequency to search for is the hydrogen line, the 21 centimeter wavelength. This is the resonance of neutral hydrogen, the most abundant substance in the universe, a natural channel for any civilization seeking to announce its presence, or, perhaps, for a technology not meant for us at all, but which we are momentarily able to overhear. Radio telescopes across Earth, from the venerable Arecibo legacy arrays to the sprawling square-kilometer array pathfinders, would be listening intently. A detection here would be monumental, but would it be proof of intelligence, or merely an unprecedented and natural astrophysical maser of a scale never before witnessed? This leads us to the third and most profound level of speculation: a synchronized optical radio outburst. Imagine the scenario: optical telescopes record a sudden dramatic flare in the comet's brightness, a surge of light that defies simple outgassing models. At that precise moment, radio observatories detect a powerful, complex pulse of 21 centimeter radiation. This is not a mere burst, but a structured, perhaps modulated, signal coincident with the visual event. Such a correlation would shatter the conventional paradigm. It would force us to confront the possibility that the wow signal, that famous, strong, undeciphered narrowband radio signal detected in 1977, was not a fleeting anomaly, but a precursor. The debate surrounding that decades-old mystery would be reignited with ferocious intensity. Was wow a message, a beacon, or the transient signature of another object like 3I Atlas passing through our own solar system, its internal mechanisms briefly activated by our Sun? The implications would force a fundamental re-evaluation of every unexplained, transient signal in our historical records, and of the very nature of the objects drifting between the stars. The perihelion window, therefore, represents a fleeting opportunity to catch a natural, or perhaps unnatural, maser in the act. It is a chance to witness a process that may be common throughout the galaxy, yet has remained invisible to us. The risk, however, is as great as the reward. The event is transient. The peak activity will last for only a short period. If the global network of observatories is not perfectly synchronized, if clouds obscure a key optical site at the critical moment, or if radio silence is maintained while the optical flare goes unseen, the moment will be lost. We will be left with an incomplete data set, another mystery to file away with all the others. The cosmos offers its secrets only to those who are watching at the right place, at the right time, and with the right questions in mind. Are we truly prepared, not just with our technology, but with our imagination, for what this interstellar messenger might reveal as it swings around our sun? Initial estimates of its nucleus, derived from its brightness and the degree of cometary activity, suggest a size between 5 and 11 kilometers. This would make it potentially the largest of the 3 known interstellar visitors, significantly larger than the previous object, 2I Borisov. This updated information, from October the 8th, 2025, is not merely a statistic. A larger nucleus implies a greater reservoir of volatile materials, a more massive engine for outgassing. It suggests the potential for far more vigorous surface activity as it undergoes the intense thermal stress of perihelion. The stage is not only set, but it is larger than we initially thought. What new phenomena might such a substantial body unleash, as it is heated to its limits? The estimated dimensions place this object between 5 and 11 kilometers in diameter, a figure that, if confirmed, would crown it the undisputed giant among our interstellar visitors. This is not merely a matter of scale, but of profound implication. A body of such magnitude carries a correspondingly vast reservoir of volatile materials, a deep, cold treasury of ices and dust accumulated in a foreign star system. Its sheer bulk suggests an internal engine of immense capacity, capable of sustaining activity across the vast, energy-sapping gulf of interstellar space. While its predecessors, Oumuamua and Borisov, were fleeting spectres, this object possesses the mass to be a more enduring, and therefore more revealing, cosmic specimen. What dormant forces, then, are contained within this frozen leviathan, and what might awaken them as it journeys into the warming embrace of our sun? According to current models of cometary science, such persistent activity is precisely what we would expect from a large, pristine interstellar object. Its substantial mass provides a greater gravitational hold on its own coma, and its thick, insulating crust of dust and organic material can shield a massive subsurface reservoir of volatile ices for eons. Scientists suggest this could be due to the object's primordial nature, a relatively unprocessed relic from the early days of its home system, now delivering a sample of that ancient material into our own. The observed outbursts could be explained by the sudden exposure of fresh ice to solar radiation, causing a violent transition from solid to gas, a process known as sublimation, which violently jets dust and gas into space. This is the conventional framework, a story written in the language of physics and chemistry that we believe we understand. But that narrative fails to account for the specific, almost theatrical nature of its brightening events. The conventional model predicts a steady increase in activity, not the sharp, unpredictable flares that have been recorded. This leads us to a more speculative hypothesis. Imagine this not merely as a lump of ice and rock, but as a complex, geological world in miniature. Its interior may not be a homogeneous mix, but a structured architecture of different ices and dust, containing sealed pockets of ancient, hypervolatile gases, materials that freeze only at temperatures near absolute zero. These would be remnants of the primordial cloud from which its star system formed, gases that have never been exposed to stellar warmth until now. As the sun's heat gradually penetrates the surface, it does not simply melt a uniform layer. It seeks out weaknesses, it finds faults and fissures. Could these be not random eruptions, but the controlled, if chaotic, venting of specific, pressurized chambers within? The data and evidence, as reported in early October of 2025, support this notion of a massive, active body. The size estimate itself is derived from a synthesis of its observed brightness, sophisticated albedo models, and the critical analysis of its stellar occultations, moments when it passed in front of distant stars, allowing astronomers to measure its silhouette with remarkable precision. Its large size is the most straightforward explanation for its ability to maintain a visible coma for such an extended period, and to produce such significant outbursts. The very brightness that makes it visible is a direct consequence of its scale. But does its size merely make it a brighter candle, or does it also make it a more complex and potentially unstable chemical reactor? Our analysis and inference must therefore proceed through escalating levels of possibility. At the first level, the principle of mass-driven persistence holds sway. The sheer volume of available frozen gases, such as water, carbon monoxide, and carbon dioxide, provides a deep well of fuel for cometary activity. The object's gravity, though weak, is sufficient to help shape the outflow of gas and dust, potentially creating more structured features like jets or fans that are sustained over weeks or months, unlike the transient, diffuse clouds of smaller comets. This foundational level explains the how of its endurance, but it does not yet touch upon the why of its sudden, violent personality. If mass were the only factor, would its activity not be more stately and predictable? This brings us to the second level of inference, the role of surface collapse and structural failure. As the subsurface ices sublimate, they leave behind voids and caverns. The overlying material, a fragile matrix of dust and rock, eventually loses its structural integrity and collapses. Such an event would be sudden and catastrophic on a local scale, exposing acres of fresh, volatile ice directly to the vacuum of space and the full intensity of solar radiation. The resulting surge in outgassing would produce a brilliant, short-lived flare, precisely matching the unpredictable brightening events we have witnessed. This is a compelling and widely accepted mechanism for cometary outbursts in our own solar system. Yet, one must wonder if even this dramatic process is sufficient to explain the most extreme events in this object's behavioral repertoire. This leads inexorably to the third and most speculative level, the concept of a jet storm. What if, instead of a single collapse, a chain reaction of structural failures occurs? A major collapse could trigger seismic waves that travel through the object's fragile core, destabilizing other volatile pockets in a cascading failure. The simultaneous rupture of multiple gas chambers would not produce a simple flare, but a storm of jets, a violent, large-scale eruption, ejecting material from numerous points across the surface. The resulting coma would be exceptionally dense and complex, a temporary, artificial atmosphere blooming around the wandering nucleus. It is within the chaotic dynamics of such an event that we can posit an even more extraordinary coincidence. Could the turbulent, high-density gas cloud of a jet storm, when bathed in the correct frequency of solar radiation, act as a natural maser, amplifying microwave emissions at specific frequencies, such as the 1420 MHz hydrogen line? The reported coincidental observation of such a signal, while unconfirmed and deeply enigmatic, forces us to confront the possibility that we are not just observing geology, but a form of transient, natural, astrophysical engineering. Are we, in our search for logical explanations, overlooking the potential for natural phenomena to mimic the signatures we so ardently hope to find? The selective consequences of its great size are twofold, presenting both a unique opportunity and a significant risk. Its large cross-section and substantial activity increase the probability of our telescopes capturing rare phenomena. A smaller object might experience a jet storm only once, and we would likely miss it. For this giant, the statistical likelihood of witnessing such an event during its passage is vastly higher. It is a larger canvas upon which the universe can paint its most exotic effects, including the hypothetical natural maser. We are afforded a front-row seat to the most active phases of an interstellar object's life. But this same scale also increases the risk of fragmentation. The immense internal pressures generated by its activity, combined with its weak gravitational binding, could ultimately tear it apart. While such an event would be a spectacular finale, the resulting cloud of debris would make long-term tracking and detailed study of the original nucleus nearly impossible, scattering the clues we so desperately seek across the orbital path. Will its great size be the key to its understanding, or the cause of its ultimate dissolution? As the object now recedes behind the Sun from our earthly perspective, a forced interlude in our observations begins throughout October and November. Our instruments fall silent, our data streams run dry. This is not an end, but a pause, a cosmic curtain drawn closed. We are left only with the lingering echoes of its past activity and the tantalizing unverified hint of a signal at 1420 MHz. What transformations will occur on its sunward side, hidden from our view? What new volatiles will be awakened by the intense, unfiltered solar wind? When it emerges back into the dark of our night sky in late November and December, a celestial phoenix returning from its stellar encounter, will it return as the same singular giant, or will we be greeted by a fragmented family of lesser bodies, each telling a smaller part of the whole lost story? The silence of the next 2 months is perhaps the most profound question of all. The celestial clockwork continues its inexorable turn, and for the observers on Earth, the months of October and November present a profound silence. The object known as 3I Atlas, our first confirmed interstellar visitor, has now slipped behind the overwhelming glare of our Sunday. It is a period of forced patience, a cosmic interlude where the object is bathed in the unobservable, searing radiance of our parent star. Yet, the astronomical community does not rest. It prepares. For in the cold, clear skies of December, a celestial re-emergence is scheduled, a moment of immense value for both optical and radio astronomy, a window that may crack open to reveal truths far stranger than we have yet imagined. What transformations might occur on this object during its solar sojourn, hidden from our prying eyes? According to current models, an object traversing the inner solar system is subjected to an intense bath of solar radiation and the constant stream of charged particles we call the solar wind. For a comet, which 3I Atlas was initially believed to be, this would typically lead to the sublimation of ices and the development of a coma and tail. Yet, the anomalous accelerations observed in its trajectory have long since cast doubt on such a simple classification. The mainstream explanation suggests that any changes upon its return would be consistent with this cometary activity, perhaps a brief period of increased outgassing as new volatiles are exposed to the solar furnace. Its brightness could simply be a product of its renewed illumination and a more favorable scattering angle for sunlight. But does a conventional coma of water and carbon dioxide ice fully explain the peculiar spectral features and the complete lack of a dust tail that has characterized this visitor from its discovery? A more speculative hypothesis proposes a far more dynamic and electrifying transformation. During its passage behind the Sun, the object is not merely being heated, it is being charged. Immersed in the million-degree plasma of the solar wind, its surface or a subsurface layer could be accumulating a significant electrical potential, much like a capacitor storing energy. As it swings back into our line of sight, this stored energy might not dissipate gently. It could be released in a sudden, catastrophic discharge, a burst of electricity interacting with the local plasma environment, a transient but powerful event. This is not simple outgassing, it is a plasma physics event on a cosmic scale. Could such an energetic exhalation be the key to unlocking the mystery of the hydrogen line emissions we have so desperately sought? The observational geometry itself fuels this anticipation. Data and predictions from July and August of 2025 have been meticulously analyzed, and they point to a significant development in the late November to December timeframe. The object's elongation from the Sun, its angular separation as seen from Earth, increases dramatically. It moves from the solar glare into a dark sky, becoming accessible for prolonged observation. This is not a subtle reappearance, it is a grand re-entrance onto the stage of the night. Radio observatories across the globe, their massive dishes tuned to the sacred 21-centimeter wavelength, the hydrogen line, have already scheduled their acquisition campaigns. They will be listening not just for a silent drifting rock, but for a voice. What will they hear when they finally re-establish contact with the wanderer? The first level of analysis will be the most straightforward, a simple assessment of its optical brightness. If it returns significantly brighter than predicted by standard models, it would be a clear indicator of a recent energetic surface event. Perhaps a landslide exposed fresh, reflective ice. Perhaps a new vent opened, jetting gas and dust into the vacuum. This would be intriguing, a puzzle piece, but it would not, in itself, be revolutionary. It would fit within the extended family of known solar system phenomena, albeit with an exotic twist. The silence on the radio bands would then be deafening, a return to the enigmatic quiet that has defined its journey thus far. But what if increased brightness is merely the prelude and not the main performance? The second, more tantalizing level would be the emergence of sporadic radio bursts. Not a continuous signal, but flickers of coherent emission at precisely 1450 MHz, or perhaps slightly shifted by the Doppler, to effect. A single, brief burst would send ripples of excitement through the community. A handful would be transformative. This scattered flaring would be the crucial experimental test for the natural maser hypothesis. A maser, a microwave amplification by stimulated emission of radiation, requires an energy source to pump it and a resonant cavity to contain and amplify the photons. The hypothetical electrical discharge, the EXA event, provides the pump. An internal structure within the object, a fissure, a cavern, or an artificially constructed waveguide could provide the cavity. Each burst would be a data point, a clue to the internal mechanics and composition of 3I Atlas. Could we be witnessing the natural if rare operation of a cosmic laser, a process that turns the faint whisper of hydrogen into a focused shout? Then there is the third level, the scenario that exists at the frontier of speculation and which would irrevocably change our place in the cosmos. Not a sporadic flicker, but a sequence. A deliberate seeming pattern of powerful, narrowband pulses, a series of mini-wow, signals echoing the legendary singular event of 1977. Such a phenomenon would shatter the paradigm of natural explanation. It would be insufficient to attribute it to a quirk of plasma physics or a resonant cavity of ice. The coherence, the repetition, the timing, coinciding with its reappearance, these factors would point towards a different kind of mechanism altogether. It would trigger not just observation campaigns, but a global, coordinated response. Every telescope capable of pointing in its direction would do so, from the Deep Space Network to the nascent orbital arrays. The winter observing schedule would become a single, unified experiment in interspecies communication. Is it possible that we are awaiting not a geological event, but a moment of reconnection? The consequences of this December reappearance are therefore starkly binary, a fork in the road of human understanding. If the object returns with a signal, even a faint and sporadic one, the winter of 2025 becomes a historical pivot point. The hypothesis of a natural maser, or something far more profound, would be put to the ultimate test. The data collected would be pored over for generations. Conversely, if it returns in utter radio silence, merely a dimming speck of reflected sunlight, the more extraordinary hypotheses will be severely constrained. The idea of an active, internally powered transmitter, or even a naturally occurring but persistent maser, would lose its most compelling observational opportunity. The Great Silence would deepen, and Three-Eye Atlas would retreat once more into the realm of the enigmatic and the unexplained, a puzzle we may not have another chance to solve for centuries. But if a signal is detected, how would we even begin to decipher its point of origin, its intended recipient, or its meaning? The answer may lie in the painstaking work of analysis that has already begun. In August of 2025, a breakthrough occurred, a refinement of a decades-old mystery. The famous WOW signal detected by the Big Ear radio telescope in 1977 was a singular, powerful burst that has never been adequately explained. For decades, its precise origin was a subject of debate, its location smeared across a region of sky. But recent analytical techniques, applying modern computational power to the original data tapes, have narrowed the probable field of view. The celestial coordinates are now more precise. More importantly, the signal's exact frequency has been pinpointed not simply at the hydrogen line's rest frequency of 1420 MHz, but at a slightly shifted 1420.726 MHz. This is not a random number, it is a specific, deliberate-looking offset. Could this refined frequency, this new, sharper address in the sky, be the key that unlocks a repeating transmission from an object we now know is passing through our neighborhood? For decades, the WOW, a signal has resided in the liminal space between artifact and contact, a singular event etched into the data from a forgotten Ohio evening. Its power was its isolation, a 6-character sequence on a computer printout that defied replication and thus definitive explanation. But now, a new number has emerged from the depths of historical analysis: 1,420.726 MHz. This is not a mere refinement, it is a key. It transposes the WOW signal from the realm of astronomical legend into a narrow, testable band of the radio spectrum, transforming a ghost into a potential target. The original mystery was its existence. The new mystery is its precise frequency. What physical process could account for such a specific and slight deviation from the universal constant of hydrogen? The canonical frequency of the hydrogen line, a beacon at 1,420 MHz, is one of the most fundamental in all of cosmology, a whisper from the neutral gas that permeates the void between stars. It is the frequency any nascent technology would likely use, and the frequency we ourselves listen to most intently. The WOW. The signal was found close to this line, but the new analysis, accounting for the specific oscillator drift of the Big Ear telescope's receivers, places it with unprecedented precision at 1,420.726 MHz. The mainstream explanation would posit an unremarkable origin, a subtle instrumental artifact, an error in the original calibration, or perhaps a previously unidentified terrestrial source, whose signal was merely reflected from a piece of orbiting debris. The signal's brevity and singular nature support the idea of a transient, human-made event. Yet, the offset, while small, is significant, a shift of a little over 300 kHz that cannot be easily dismissed as noise. What if this offset is not an error, but a message in itself? This leads us to our first speculative hypothesis. Consider the Doppler effect, the same principle that causes a siren's pitch to change as it passes by. A signal originating from a technologically sophisticated source would not be broadcast from a stationary platform. It would be transmitted from a planet orbiting a star, from a spacecraft moving through the interstellar medium, or even from a probe navigating the galactic currents. The velocity of such a source relative to our solar system would impart a minute shift to the transmitted frequency. The newly refined frequency of 1,420.726 MHz could be the hydrogen line, but shifted by a consistent velocity. A simple calculation suggests a relative motion of approximately 68 kilometers per second. This is not an implausible speed for an object within our galactic neighborhood, moving with the differential rotation of the Milky Way. Could the WOW signal be the first clear Doppler signature of an interstellar source passing through our line of sight, its frequency subtly pushed by the stellar winds and magnetic fields of the galaxy? The implications of this refined frequency are profound and operate on three distinct levels of analysis. At the first and most fundamental level, this new precision provides a definitive coordinate in the radio spectrum. It allows modern instruments, like the Allen Telescope Array or the upcoming Square Kilometre Array, to train their collective sensitivity on an exact point, to stare at the coordinates in Sagittarius with a new and focused intent. No longer are we searching a band, we are monitoring a line. This transforms the search from one of broad discovery to one of targeted verification. If the signal was a one-time event, this refinement may seem academic, but if it is a persistent, repeating beacon, or even an intermittent one, we now know precisely where to listen. How many past observations have we discarded because our filters were too wide, because we were listening for a shout in 5, a narrow band, and missed a whisper on a specific frequency? At the second level, this frequency allows us to test a specific model against a known celestial object. The refined position in the sky, when combined with this precise frequency, creates a unique fingerprint. Recent analyses have cross-referenced this data with modern hydrogen line catalogues, which map the intricate structure of neutral hydrogen gas in the direction of the Sagittarius constellation. The WOW signal's location does not correspond to a known powerful natural emitter like a pulsar or a maser, but it does lie within a complex region of interstellar gas. The mainstream view is that the signal could have been an unusually intense and fleeting amplification of background noise by a yet unknown astrophysical process within this gas cloud. However, the speculative hypothesis pushes further. Could we now look for a moving object whose trajectory and velocity would align with this Doppler shift? Could the path of an interstellar object, like the enigmatic Oumuamua or its successor, Comet Atlas, be backtraced to see if its kinematic properties could produce such a frequency offset at that specific time and location? The data from the Big Air, when fully reanalyzed, may provide the temporal and spatial resolution to begin such a celestial triangulation. Is it possible that we have already observed the messenger, but failed to connect it to the message? The third and most transformative level of analysis concerns the very nature of scientific discovery. A single, unrepeatable event is an anomaly. A repeatable one is a phenomenon. The ultimate value of this frequency refinement is that it provides the recipe for replication. If, by some extraordinary chance, a signal is ever again detected at these exact celestial coordinates, at this exact frequency of 1420.726 MHz, the WOW signal would be instantly transformed. It would shed its status as a curio and become a datum, a point of persistent and predictable contact. The search is no longer for another WOW. It is for a confirmation of a specific signal profile. This shifts the entire paradigm of the investigation from historical analysis to active, forward-looking observation. What would it mean for our place in the cosmos if a signal, once thought to be a fleeting ghost, was found to be still broadcasting, waiting for us to finally tune our instruments to the correct station? The consequence of this refinement is that 1420.726 MHz becomes a treasure map, a set of coordinates leading to a potential discovery of incalculable value. Yet, we must confront the sobering possibility that the treasure itself may not be what we imagine. The most rational conclusion, should the signal be rediscovered, is that it originates from a natural source. A previously undetected type of astrophysical maser, a natural laser operating at the hydrogen frequency, could produce an intense, narrowband signal. The complex structure of the hydrogen gas in the galactic plane toward Sagittarius provides a plausible environment for such a phenomenon. The signal's intensity and narrow bandwidth are consistent with a maser's emission. In this view, the signal remains a spectacular natural event, a cosmic coincidence that mimicked the expected signature of an artificial broadcast. But does the existence of a natural explanation diminish the value of the search, or does the relentless pursuit to confirm it, to understand the mechanics of such a potent natural emitter, constitute a scientific achievement of equal magnitude? The journey to retrieve the signal, to point our most powerful dishes toward that patch of sky and listen on that specific frequency, is itself the greater prize. It drives technological innovation, refines our methodologies, and forces a collective contemplation of our position in the universe. The value is not solely in the potential answer, but in the quality of the questions we are compelled to ask along the way. The refined frequency is the catalyst for a new, more sophisticated phase of the search for cosmic company. It compels us to look not just for a signal, but for the context of that signal, for the Doppler shift that hints at a journey, and for the repetition that implies persistence. And so, with this new number as our guide, we are drawn back to the original data, to the very fingerprints of the event, to see what other secrets the past may hold when examined with the tools of the future. What if the full story of that August evening has been waiting, not in the summarized data, but within the raw, unprocessed logs of the Big Ear telescope? A story that can only be read if we can preserve it before time erases it completely. The vast and silent archive of the Big Ear radio telescope, a repository of cosmic whispers from a bygone era of exploration, is slowly being roused from its analog slumber. In anticipation of its 50th anniversary in 2027, a monumental effort is underway to digitize its entire holdings, to transform fragile magnetic memories into an immutable and open digital legacy. This is not merely an act of preservation, it is an invitation. When memory becomes open data, the legendary WOW signal is, in a sense, placed back upon the scientific operating table, its enigmatic nature exposed to the scalpel of modern analytical tools and the collective intellect of a global community. Could it be that within these aging tapes, nestled amidst the cosmic static, lies a forgotten companion to the WOW signal, a spectral echo that was missed not due to its weakness, but due to a temporal miscalibration? According to current models of data analysis from the 1970s, the methodology was necessarily constrained. The search for extraterrestrial intelligence was in its infancy, a process reliant on human vigilance, scanning paper charts for singular anomalies. The announcement on August 27, 2025, of the Comprehensive Digitization Plan, complete with FAIR data principles, ensuring findability, accessibility, interoperability, and reusability, represents a paradigm shift. It promises a re-examination of the entire observational record with machine learning algorithms capable of discerning patterns and correlations that would have been utterly invisible to the astronomers of that time. This is a systematic hunt for the anomalous, conducted with a sophistication that was science fiction in the 1970s. But what if the original processing, focused on a specific signal profile and a certain integration time, inadvertently filtered out a more complex truth? The speculative hypothesis emerges that the WOW signal was not a solitary event, but rather the brightest peak in a sequence of fainter, repeated transmissions. A companion signal, perhaps temporally offset or possessing a slightly different frequency drift, could have been algorithmically discarded or simply lost in the noise floor. A ghost in the machine, waiting half a century for its moment of discovery. Is it possible that our greatest cosmic mystery has been, all this time, a fragment of a larger, more complex conversation? The analytical journey through this newly liberated dataset will likely unfold across three distinct levels of interpretation. The first, and most conservative, level may conclude that there is nothing new to be found. The WOW signal remains a magnificent and frustrating isolate, a single, brilliant data point in a sea of silence, its singularity reaffirmed by the most powerful analytical tools of the 21st century. This would be a validation of the original findings, yet a profound disappointment to those seeking a deeper narrative. Could the universe truly be so capricious as to offer only one fleeting glimpse of a phenomenon we so desperately wish to understand? The second level of analysis offers a more tantalizing prospect, the discovery of faint, ambiguous clues. These would not be definitive signals in their own right, but statistical curiosities, faint clusters of energy that cluster around the frequency and celestial coordinates of the WOW event. They would be insufficient to claim a discovery, yet compelling enough to reorient entire observational campaigns. Radio telescopes across the globe might once again turn their dishes toward the 1420 MHz hydrogen line, not in search of a replica, but to investigate the possibility of a sporadic, repeating source. What if the key to unlocking WOW is not a louder signal, but a patient, long-term study of its quiet neighborhood? The third, and most revolutionary, level would be the identification of a weak, intermittent sequence of signals both before and after the August 15, 1977 event. This would fundamentally reshape the mystery. It would suggest not a one-time technological burst, but a persistent, natural astrophysical phenomenon of an unknown type. A pulsar with an unprecedented modulation, a quasar with a previously undetected periodic flare, or some other celestial engine operating on principles not yet described by our physics. The implication that a natural source could mimic a potential artificial signal so perfectly would force a complete reassessment of the criteria used in the search for extraterrestrial intelligence. Does this mean that the very signature we seek is more common and more enigmatic than we ever imagined? The consequences of this open data paradigm are as profound as the potential discoveries themselves. It democratizes the search, empowering a global army of citizen scientists and computational astronomers to sift through the cosmic sands, each with their own unique perspective and analytical approach. The risk, of course, is a cacophony of premature interpretations and false alarms, the inevitable noise that accompanies any signal of great significance. Yet, the benefit is the establishment of a new standard of radical transparency for SETI, a field that has long grappled with the challenge of extraordinary claims. In this new era, the burden of proof is not borne by a single institution, but by the collective scrutiny of the world. As we prepare to dissect this digital ghost, we must ask, will the story of WOW be one of closure, or the beginning of a far more complex and layered mystery? For the true context of any signal lies not just in its data, but in the celestial stage upon which it was projected. The classic record now aims to bind its test to a specific alignment, correlating its direction with the known paths of celestial wanderers like Comet 3I Atlas. Using this foundational data to fuel intricate simulations that rewind the orbital clock. The WOW signal arrived from the direction of Sagittarius, a star-rich region toward the galactic center, a location both promising and problematic. Mainstream astronomy suggests this area is a fertile ground for unknown astrophysical phenomena, its density of stars offering a multitude of potential natural explanations. The original Big Ear observations provided two beams that scanned the same point in the sky several minutes apart. The signal appeared in one and not the other, suggesting a transient source. But what celestial object moves or varies in such a manner? The speculative hypothesis considers a more deliberate origin, that the signal's location was chosen not despite its crowded nature, but because of it. A civilization wishing to broadcast its presence might aim for a visually striking region, a landmark on the galactic map, ensuring the message is seen against a backdrop of cosmic significance. Could the dense starfields of Sagittarius be the intended billboard for a message we have only just begun to decode? The upcoming orbital simulations, reverse engineering the positions of every known object from that moment, seek to eliminate the possible, leaving only the truly anomalous. But if all natural candidates are ruled out, what are we left to contemplate? The sky itself holds the answer, a silent witness to an event that continues to challenge our place in the cosmos. The galactic plane in the direction of Sagittarius is a dense and luminous river of stars, gas, and dust. It is here, within the sprawling complexity of our galaxy's central bulge and the intervening spiral arm, that the interstellar medium becomes a thick, cosmic fog. This region is a primary reservoir of neutral atomic hydrogen, the most abundant element in the universe, which perpetually emits its faint, characteristic whisper at a frequency of 1420 MHz, a 21 centimeter line that paints the structure of the Milky Way in radio light. It was toward this specific, crowded stellar neighborhood that the Big Ear radio telescope at Ohio State University was listening on the 15th of August, 1977, when it recorded the signal now immortalized as the "wow." According to current models, the sheer column density of neutral hydrogen along this line of sight provides a fertile environment for the natural amplification of radio waves, a phenomenon known as a maser effect, where turbulent gas clouds can act as cosmic lasers, intensifying weak signals into detectable bursts. But could such a natural process, however energetic, account for the signal's remarkable intensity, its narrow bandwidth, and its tantalizing singular nature, a shout that has never been repeated? What if the stage itself is not merely a backdrop, but an active, resonant instrument? This leads us to a more speculative hypothesis. Imagine this entire sector of space not as a chaotic cloud of gas, but as a vast, structured instrument, a galactic organ of neutral hydrogen. Within this organ, the dense clouds and filaments of gas act as resonant cavities, waiting for a catalyst. The passage of an interstellar object, like the enigmatic Comet 3I Atlas, could serve as that catalyst, its gravitational field, or its own extended cometary atmosphere brushing against these cosmic keys, plucking the 21 centimeter string and generating a transient, powerful note. The 1977 data firmly anchors the wow signal to this specific galactic longitude in Sagittarius, and all sky surveys of neutral hydrogen, such as the Leiden-Argentine Bond Survey and the more recent HI-4PI project, reveal a patchwork quilt of gas clouds with complex differential velocities. These are not smooth, homogeneous structures, but a tangled web of filaments and sheets, a necessary mosaic of data points for any attempt at reverse simulating an object's trajectory and its potential interaction with the interstellar medium. If a string is plucked, does the instrument not leave a signature in the resulting chord? At the first level of analysis, the explanation appears straightforward. The exceptional thickness of the neutral hydrogen layer in the direction of the galactic center provides a plausible explanation for a naturally amplified signal. The greater the path length through this amplifying medium, the higher the probability that a background signal, perhaps from a distant quasar or a particularly active stellar nursery, could be boosted to the observed intensity. This is a well-established principle in radio astronomy, where the line of sight through a spiral arm can magnify certain phenomena. Yet, if this were the sole mechanism, why would such powerful, narrowband maser events not be detected more frequently across the densely populated plane of the galaxy? And why would this one stand in such stark, solitary contrast to the perpetual radio silence that has followed? Is our understanding of interstellar maser stability fundamentally incomplete? Progressing to a second, deeper level, we must consider the dynamics of the gas itself. The Sagittarius arm is not a static structure. It is a river of stars and gas, flowing through the galactic gravitational potential. Within this flow, there exist regions of shear, compression, and turbulence, cosmic knots, where the velocity fields of different hydrogen clouds collide and interact. Such a dynamic interface could create a temporary, focused region of coherent emission, a knot of intense maser activity that aligns perfectly with our line of sight for a brief moment. The wow! Signal's frequency drift, or lack thereof, could be a key to unlocking the velocity structure of such a knot. But does the known physics of turbulent interstellar gas truly allow for the generation of a signal that was both so spectrally pure and so astonishingly strong, a signal that mimicked the expected signature of an artificial, narrowband beacon? Could the galaxy itself be capable of such precise, if fleeting, orchestration? This brings us to the third and most speculative tier of inference, where we introduce a specific, known actor onto this galactic stage. The first documented interstellar object to pass through our inner solar system, Comet 3I Atlas. Its origin, while not definitively traced to the Sagittarius constellation, serves as a proof of concept that such travelers exist and cross the vast distances between stars. Now, consider the ion tail of such an object, a stream of ionized gas extending millions of kilometers, swept by the solar wind and the interstellar radiation field. If an object like 3I Atlas were to pass through a particularly dense and kinematically complex knot of neutral hydrogen in the distant reaches of its journey, the interaction between its cometary plasma and the surrounding cloud could be far more intricate than simple gravitational perturbation. The plasma could act as a tuning fork, exciting the hydrogen in a very specific, coherent manner, or perhaps even modulating a pre-existing natural maser. The unique conditions of this interference, the specific density of the cloud, the velocity of the object, the composition of its tail, could recreate a wow-like signal, a single note played according to a galactic rhythm we are only beginning to perceive. Is it mere coincidence that the first strong candidate for an artificial signal came from a region supremely suited for such a complex natural interaction? Or are we witnessing the same phenomenon through two different interpretive lenses? The implications of this line of reasoning are profound and demand a selective shift in our search strategies. If the direction of Sagittarius is indeed a workshop for anomalous 21 centimeter emissions, then our approach to the search for extraterrestrial intelligence must evolve. The traditional method of pointing telescopes at individual stars seems almost myopic when confronted with the possibility that the medium between the stars itself may be the source of the most tantalizing signals. A new paradigm emerges, a SETI environment model, where the map of galactic neutral hydrogen becomes as crucial as any star chart. In this model, the search for technosignatures and the study of natural signatures are not parallel but intertwined endeavors, each informing and validating the other. If the universe is playing a grand symphony on the instrument of the interstellar medium, should we not be listening to the entire orchestra, rather than waiting for a single soloist to announce themselves? This conceptual framework, however, remains a theoretical construct until it can be tested against new observational data. The universe, in its providence, may be offering us precisely such an opportunity. The predicted return of Comet 3I Atlas to the inner solar system in late November and December of 2025 presents a unique and unprecedented experimental window. This is not a repetition of the 1977 event, but a controlled experiment made possible by a known interstellar interloper. Could we, therefore, design a campaign to finally listen to the interaction between a comet's tail and the silent sea of hydrogen through which it sails? The proposal is for a coordinated, multi-observatory campaign at the 21 centimeter line, a synchronized effort across the globe to track 3I Atlas as it brightens. The goal would be twofold: to meticulously search for any anomalous radio emissions emanating from the comet itself or its immediate environment, and to use the comet as a probe to study the properties of the local interstellar medium it is traversing. By employing very long baseline interferometry with multiple radio telescopes, we could achieve unprecedented resolution, potentially distinguishing between a signal generated by the comet's nucleus and one stimulated in its extensive ion tail. This campaign must be phased with optical observations, as the comet's activity and tail structure are critical parameters for interpreting any radio data. The window for optimal observation, as indicated by analyses from Live Science and the European Space Agency, falls between the 7th and 12th of October, 2025, a period of heightened visibility before its closest approach. What secrets might we unlock by turning our most sensitive ears toward this wanderer, not merely as an object of study, but as a potential key to a 48-year-old mystery? The potential outcomes are binary, yet both revolutionary. If we detect a transient, narrowband signal at 1420 MHz associated with 3I Atlas, it would not immediately prove the existence of extraterrestrial intelligence, but it would provide the first concrete evidence that interstellar objects can generate such signals through natural, if complex, plasma and neutral gas interactions. This would validate the galactic organ hypothesis for the wow signal and fundamentally alter our interpretation of that historical event. Conversely, if we monitor the comet throughout its passage and detect nothing out of the ordinary, it would not disprove the hypothesis, but it would place stringent limits on the conditions required for such an emission, pushing the wow signal further into the realm of the extraordinary and perhaps the artificial. In either case, we move from speculation into the realm of empirical science. Are we prepared to use this celestial visitor as a probe, not just of its own nature, but of the very fabric of galactic communication? The coordinated radio campaign of late 2025 is more than an observation. It is an interrogation of the cosmos, a direct question posed to the void, asking if the music of the spheres is a melody of nature or something else entirely. The answer lies in synchronization, when the lens and the antenna speak the same language of time. As the final months of 2025 approach, a unique astronomical campaign prepares to listen. The target is the interstellar visitor, Comet 3I Atlas, and the method is a meticulously coordinated global effort, a symphony of observation where optical telescopes and radio antennas are tuned to the same precise instant. This is not merely simultaneous watching, this is a fundamental unification of perception, an attempt to see and hear the universe as one coherent phenomenon. For if light and radio waves are but different expressions of the same electromagnetic truth, then their combined gaze might reveal secrets invisible to either alone. What profound unity might we discover when we finally learn to perceive in concert? The core of this endeavor is the hydrogen line, that fundamental whisper of the cosmos at 1420 MHz. It is the resonant frequency of the neutral hydrogen that permeates the void, a universal constant used for decades to map the grand spiral arms of our own galaxy and to listen for potential signals from other worlds. Yet, for 3I Atlas, the search narrows, with exquisite precision, not to the line itself, but to a specific, shifted frequency, 1420.726 MHz. This calculated offset accounts for the Doppler shift induced by the relative motion between the Earth and the comet, a correction born from our understanding of classical physics. It is a testament to our technical prowess, our ability to predict the universe's behavior. But what if our predictions, however precise, are based on an incomplete model of the object we study? The observational window is narrow and unforgiving, opening in late November and December of 2025, immediately after the comet emerges from its conjunction behind the Sunday. This emergence from solar occultation is critical, for it presents the object as if newborn to our instruments, free from the sun's overwhelming radio interference. The strategy is one of overwhelming coordination. A network of professional observatories like the venerable Allen Telescope Array will join forces with a global legion of amateur astronomers, their collective instruments capturing not just intensity, but high-time resolution data, full spectroscopy, and polarization states. This creates a multi-dimensional portrait of any emission, a forensic-level analysis of the comet's radio voice. Could such a distributed vigilant network finally catch the ephemeral signal that has eluded us for so long? The speculative hypothesis, the one that fuels the imagination behind this immense logistical effort, posits an intrinsic clock within 3I, Atlas itself. This is not a clock of gears and springs, but a natural, or perhaps not so natural, oscillator, a rhythmic engine that causes simultaneous optical brightening and radio emission to pulse at a predictable interval. The chaotic outgassing of a typical comet, driven by the volatile and unpredictable heating of its ices, would not produce such a clean, periodic signal. The rhythmic brightening observed in previous apparitions defies simple cometary behavior. If such a clock exists, then the key is not to stare blindly into the void, but to be looking at precisely the right time, with the right instruments, synchronized to its hidden cadence. Is it possible that we are not searching for a random event, but attempting to eavesdrop on a meticulously timed broadcast? According to current models, a null result from the campaign would be the most likely, and in some ways, the most scientifically clarifying outcome. Detecting nothing beyond the expected, stochastic noise at the targeted frequency would powerfully constrain the more exotic interpretations. It would strongly narrow, perhaps even collapse, the scenario that equates 3I Atlas with the legendary WOW signal, a transient event of unknown origin detected in 1977. A non-detection would forcefully argue that this interstellar traveler is, despite its unusual orbit, a remarkably quiet and mundane body, its mysteries confined to the realm of chemistry and dynamics rather than artificial or coherent radio emission. But does the absence of evidence truly constitute evidence of absence, or does it merely reflect the limitations of our current listening posture? Should the campaign detect a signal, the interpretation will begin, and it will do so at distinct and escalating levels of implication. The first level of analysis would be the discovery of a brief, narrow-band spike, a transient whistle in the cosmic static. The mainstream scientific explanation would immediately point towards a natural maser. Intense jets of water vapor or other molecules, excited by the sun's radiation, could theoretically produce coherent amplification of radio waves, creating a powerful, narrow-band burst much like a laser operates with light. Interactions between the comet's coma and a localized cloud of neutral hydrogen could generate a similar, naturally occurring signal at precisely the hydrogen line frequency. It would be a remarkable discovery, the first confirmed natural maser from an interstellar object, yet one that remains firmly within the boundaries of known physics. Yet, if it is a natural maser, why would its timing be so precise, so seemingly locked to an internal rhythm that also modulates its light? The second, more profound level of analysis would be triggered by the detection of not just one spike, but a sequence of them, a repeating pattern. This would immediately elevate the finding from a curious anomaly to a systematic phenomenon. If these repeating bursts further exhibit a Doppler shift that perfectly mirrors the calculated orbital trajectory of 3I Atlas, the case for an intrinsic, clock-like mechanism becomes overwhelming. Such a precise correlation between the signal's changing frequency and the object's motion through space would provide a stunningly detailed data set. It would open an entirely new battlefield for the science of interstellar planetesimals, allowing us to probe its rotation, its internal structure, and the possible driving mechanism behind this regular pulsation with unprecedented accuracy. But what natural engine, residing deep within a small icy body, could possibly maintain such metronomic precision across the light years? The consequences of a clear detection are as immense as the risks are subtle. The opportunity is to construct the first true radio portrait of an interstellar visitor. This would not be a simple image, but a dynamic profile of its emissions, a fingerprint of its physical processes. It would transform 3I Atlas from a faint point of light into a complex, vibrating entity with its own unique voice. Yet, the parallel risk is the chasm between scientific evidence and public expectation. In an age of instant communication, the announcement of a repeating signal from an interstellar object would ignite a firestorm of speculation, quickly outpacing the cautious, methodical language of scientific analysis. This places a profound responsibility on the scientific community to communicate with rigor and clarity, to tell the story with accuracy without extinguishing the public's sense of wonder. How do we share the profound mystery of a potentially natural yet deeply strange phenomenon without allowing it to be prematurely cast as a definitive message from another civilization? The very act of this coordinated search, this marriage of optical and radio astronomy, represents a paradigm shift in our approach to the unknown. We are no longer passive observers of the cosmos. We are active interrogators, using the full spectrum of our technological capabilities to ask a single, pointed question of a celestial wanderer. The synchronization of our instruments is a reflection of our desire to find synchronization in the universe itself, a hope that behind the apparent chaos of cometary activity lies a deeper, more fundamental order. Whether that order is born from the intricate physics of resonating ices or from something far more speculative, the campaign will have irrevocably advanced our methodology. And so, as the world's telescopes and antennas turn in unison toward a point of light emerging from the sun's glare, we are left to ponder. Are we merely witnessing the intricate dance of a natural body? Or are we, for the first time, correctly setting our clocks to keep an appointment made long ago and far away? This meticulous preparation, however, inevitably leads to a more contentious and profound debate. If a signal is found, how do we determine its ultimate origin? The scientific process demands natural explanations, yet the possibility, however faint, of a different source beckons from the edges of consensus. What happens when a respected voice within the astrophysical community looks at the same data and calculates not a probability of 0, but a tangible chance that we are witnessing something not entirely born of nature? If the natural origin of the interstellar object designated 3I Atlas is accepted with 99% certainty, it is that final, fragile 1% that commands our most profound attention. For in the vast statistical silence of the cosmos, a probability that is not 0 is a doorway, however narrow, through which we can peer into the realms of the truly extraordinary. This sliver of doubt is not a failure of our models, but a testament to the rigor of our scientific method, which compels us to ask, what if, against all odds, we are not merely observing a cosmic vagabond, but an artifact? The mainstream scientific explanation, grounded in the observations from the Hubble Space Telescope in July and August of 2025, and later reinforced by the Trace Gas Orbiter, paints a coherent picture. The data aligns with the behavior of a comet, an ancient conglomerate of ice, dust, and rock, venturing from the profound chill of interstellar space into the warmth of our inner solar system. Its outgassing, the sublimation of volatile ices, creating a temporary atmosphere and tail, accounts for the observed changes in brightness and coma. The orbital refinements provided by the European Space Agency and NASA in October of 2025 further cement its trajectory as a product of gravitational mechanics, a path dictated by the sun's pull and the object's own initial velocity. According to current models, 3I Atlas is a messenger from another star, a natural body whose composition might reveal the universal commonality of planetary formation. Yet, does a comfortable explanation necessarily equate to a complete one? This is where the 1% breathes, giving rise to speculative hypotheses that challenge our very frame of reference. Imagine, for a moment, that this is not a comet, but a derelict, a light sail, conceived by a civilization long since turned to dust, on a voyage that began millennia ago. Its tattered, reflective membrane, designed to catch the momentum of starlight, could now be fracturing under the sun's radiation, creating the peculiar spectral signatures and the brief, sharp variations in luminosity. Alternatively, consider the possibility of a hollow, metallic core, a structure whose geometry is not that of a random accretion, but of a designed vessel. Could the radio frequencies detected, the subtle resonances within the object, be the result of an internal cavity acting as a resonant chamber, an echo of its artificial origin? These are not claims, but contemplations. What if the very laws of physics we use to identify natural phenomena are the same laws an intelligence would use to construct a probe meant to endure an eternity between stars? The debate intensified in the final months of 2025 as data from multiple sources converged. A minority of researchers, perhaps 30 to 40% of those closely studying the object, pointed to persistent anomalies. They noted the object's short-term brightness variations, which occurred with a rapidity that seemed at odds with the relatively slow process of cometary outgassing. They analyzed the geometry of its coma, the cloud of gas and dust surrounding it, and suggested a degree of structured symmetry, an ordered coma that seemed to defy the typically chaotic and uneven ejection of material from a natural ice body. The precise orbital constraints published in October of 2025 were seen by some not just as a refinement of its path, but as a potential clue that its trajectory had been subtly, intelligently guided in the distant past. The majority of the astronomical community, however, stood firmly by the cometary hypothesis, citing the overwhelming consistency of the Hubble and TGO data with known physics. But when faced with a confluence of minor irregularities, at what point does a collection of imperfections begin to suggest a different kind of perfection? To navigate this labyrinth of possibility, we must structure our analysis across three distinct, escalating tiers. The first level is the null hypothesis. There are no artificial characteristics. The object behaves exactly as a comet should, and the debate is closed. This is the most probable, and thus the most scientifically conservative, conclusion. It is the bedrock upon which our understanding of interstellar objects is built. But can we ever be truly certain we have exhausted every conceivable test for artificiality? The second level introduces ambiguity. Here, we encounter signs that are suggestive but not conclusive. Perhaps the light from 3I Atlas exhibits an unusual degree of polarization, a specific alignment of light waves that could be consistent with reflection from a smooth, manufactured surface, rather than scattering from fine dust. Or maybe its brightness fluctuates with a faint recurring periodicity, a rhythm that whispers of mechanism rather than random eruption. At this tier, the debate is not closed. It is prolonged, demanding more sensitive instruments and more creative analytical techniques. It is a state of sustained, and perhaps perpetual, uncertainty. How long can science sustain a question that offers no clear path to an answer? Then, there is the third level, the realm of the profound. This is triggered by the detection of a patterned signal, a sequence of radio or optical emissions that repeat in a manner defying natural stochastic processes. A encoded message. Such a discovery would shatter the null hypothesis irrevocably, swinging the 1% probability into a near certainty and opening the door to the confirmed detection of a technosignature. It would be the moment our place in the universe is forever altered. Yet, if such a signal were discovered, buried within the noise, would we possess the intellectual and cultural maturity to comprehend its meaning, or even to recognize its intent? The practical consequence of entertaining this 1% possibility is not a descent into unscientific fantasy, but the rigorous, the application of the principle of conserved skepticism. By refusing to completely dismiss the artificial hypothesis, no matter how improbable, we force ourselves to design more stringent observational campaigns. We learn to distinguish more clearly between what is scientifically possible and what is merely media allure. This disciplined approach prepares our methods and our minds for the day when the anomaly is not a fleeting 1%, but an undeniable 100. For if we are not prepared to recognize the extraordinary, might we simply overlook it when it finally arrives? And as we contemplate the nature of this visitor, a more immediate, physical question emerges, one that will test the limits of its structure, be it natural rock and ice or something else entirely. The calculations published on the 11th of October, 2025, point to a moment of existential crisis, a close encounter with our star that threatens to tear the object asunder. The question of its fundamental composition, and perhaps its origin, may soon be answered not by a subtle signal, but by a violent and definitive act of disintegration. Will the object's impending destruction near perihelion reveal a fragile core of primordial ice, or the stubborn integrity of an engineered hull? The moment of perihelion is the ultimate test of endurance for any comet, a trial by celestial fire, where the combined fury of solar radiation and immense tidal forces reaches its crescendo. For countless comets, this passage proves fatal, their fragile structures succumbing to the onslaught and disintegrating into scattered clouds of ice and dust. The case of the interstellar visitor, 3I Atlas, as it approaches its own date with our star, presents a profound puzzle. Did its fragmentation begin before this moment of supreme stress, or was it the consequence of it? The very timing of its breakup holds the key to understanding the fundamental architecture of this traveler from another star. According to current models, a comet's nucleus is a fragile aggregate of ices and dust, often described as a primordial dirty snowball. As it nears the Sun, subsurface ices, primarily water and carbon monoxide, sublimate, building up internal pressure. Tidal forces then exert a shearing stress, pulling the object apart. This standard sequence would suggest the most significant fragmentation events should cluster tightly around the perihelion passage itself, the point of maximum environmental stress. The initial light curve data from early October showed only minor fluctuations, consistent with the steady, predictable increase in outgassing activity from a slowly warming, intact body. But what if the structure of 3I Atlas was not that of a simple consolidated snowball? What if instead it was a cosmic pumice stone, a labyrinthine honeycomb of caverns and chambers carved from exotic ices over eons in the deep cold of interstellar space? In such a fragile architecture, a critical failure would not require the peak fury of perihelion. A single structural collapse, a pillar of ice giving way in the gentle warmth of the approaching sun, could trigger a catastrophic chain reaction. A cascading collapse of these caverns would generate a sudden, immense shower of icy fragments, their fresh surfaces flashing into vapor and creating a brilliant, short-lived outburst. This explosive release of energy and charged particles could, in theory, excite the surrounding plasma, inadvertently generating a transient, repeating burst of radio waves, a natural yet startling signal. Could the initial breakup of this object have been not a tearing apart, but a crumbling from within, a silent, structural failure that predated its greatest trial? The data from the 11th of October, 2025, serves as a crucial warning. An article published in that week detailed the elevated risk of fragmentation for 3I Atlas, as it closed to a distance of approximately 203 million kilometers from Earth around the 29th and 30th of October. It strongly recommended a coordinated observational campaign, focusing on the morphology of the comet's tail and the polarization of its light, as these are the most sensitive diagnostics of a nucleus undergoing stress and potential disintegration. The pre-perihelion light curve, while generally trending upward, already exhibited those subtle telltale oscillations, minor brightening events that could be the first whispers of instability. Were these flickers merely the result of normal, localized jet activity, or were they the signature of the first few bricks falling in the wall of its integrity? To decipher this, we must consider the event through a hierarchy of potential outcomes, a ladder of escalating disintegration. The first and most conservative level posits that the comet did not fragment at all. The observed fluctuations were simply the result of its steadily increasing activity as new regions of its surface were exposed to sunlight. The coma would grow brighter and more structured, but would remain anchored by a single, dominant nucleus, its voyage through the inner solar system, a testament to its surprising cohesion. Is it possible that our expectations of fragility are misplaced, and this visitor is far more robust than any comet of local origin? The second level of analysis suggests a minor fragmentation event. Here, the comet sheds a few sizable fragments, perhaps a single large piece or a small cluster. This would manifest as a distinct, short-lived surge in brightness, a flare easily visible in the light curve, and the possible emergence of secondary condensation points within the coma, visible to high-resolution telescopes. The overall structure of the comet would remain largely recognizable, but now, with companions trailing in its wake, this scenario is the most common outcome for stressed comets in our own solar system. But if this is what occurred, what unique properties of interstellar material would be revealed in the spectral signature of these newly exposed fragments? The third, and most dramatic, level is that of a major fragmentation. This is not merely the shedding of pieces, but a fundamental structural failure of the nucleus. The comet's core would dissolve into a swarm of multiple nuclei, a cloud of glittering debris. The coma would become a dense, chaotic shroud of dust and gas, potentially enveloping the fragments and creating a prolonged, brilliant display. The sheer volume of released gas, particularly water vapor, could interact with the solar wind and radiation in a way that stimulates a natural maser emission, a coherent, intense amplification of specific radio frequencies, a beacon born from destruction. Such an event would be a celestial spectacle of the highest order. Yet, if the disintegration is too complete, does the very chaos that creates this laboratory for studying pristine material also destroy our ability to interpret its findings clearly? This leads us to the profound and selective consequences of fragmentation. A breakup, particularly a major one, offers an unparalleled opportunity. It is a spontaneous dissection of an interstellar object, exposing interior material that has been shielded from all stellar influences for millions, perhaps billions, of years. We would be granted a direct sample of the building blocks of a planetary system born around another star, a chance to analyze its isotopic ratios, its complex organic chemistry, and the very structure of its ices, without the need for a spacecraft to land and drill. It is a gift of pure, unadulterated knowledge, delivered to our doorstep by the cosmos itself. Yet, this gift comes with a significant risk. The chaotic, energetic environment of a disintegrating comet is a cacophony of emissions across the electromagnetic spectrum. The very radio bursts or other anomalous signals we might be hoping to detect, signals that could be misinterpreted as something other than natural, would be drowned in this self-generated noise. A clear, pristine signal from an intact object is a simple message. The roaring static of a dying comet is a symphony of confusion. Could a spectacular fragmentation of 3I Atlas inadvertently mask a subtler, more profound signal within its debris, or even generate a false positive that echoes the most tantalizing mysteries of our past, like the famed WOW signal? The answer to this may not lie in our observations from Earth alone, for our perspective is but a single viewpoint in the solar system. And as we ponder the fate of 3I Atlas, from our terrestrial vantage point, a new data stream has begun, one that offers a critical, second perspective on this interstellar drama. The announcement came via the European Space Agency, disseminated through the scientific press on the 12th of October, 2025. It confirmed a series of coordinated observations from a fleet of assets in orbit around Mars. From the red plains of another world, a separate set of eyes now watches the approach of the visitor. This extraterrestrial baseline provides a crucial parallax, a means to triangulate its position, motion, and activity with unprecedented precision, allowing for a more refined calibration of all our measurements. What new secrets of its approach and its initial breakup will be revealed when we see it, not just from one world, but from two. On the 12th of October, 2025, a silent, frigid world witnessed a spectacle unseen for millennia. The thin, carbon dioxide-dominated atmosphere of Mars, a veil barely 1% as dense as Earth's, began to glow. From the perspective of orbiters like the European Space Agency's Mars Express and NASA's MAVEN, the void above the Martian terminator ignited with a cold, brilliant fire. The cause was not a meteor shower born of the local system, but the passage of an interstellar visitor, the object designated 3I Atlas, as it plunged through the inner solar system. Its immense, dusty tail, a stream of primordial material from a system light-years away, was not merely reflecting sunlight, but was set ablaze by a unique atmospheric lens. The tenuous Martian air, insufficient to burn a human, proved dense enough to create a transitional scattering effect, a cascade of collisions that excited the fine dust particles to incandescence. The resulting time-lapse observations were not of a simple streak, but of a blossoming, ethereal pyrotechnic display, a cold firework in the void. If a world so barren and distant could provide such a pristine vantage point, what other cosmic secrets are we missing from our singular, earthly perspective? The initial data, summarized in a swift yet meticulous ESA press release, confirmed the essential facts. A faint, fast-moving point was tracked across multiple sequential imaging passes, its velocity and trajectory precisely consistent with the refined orbital calculations for 3I Atlas. This was not an anomalous blip. It was a confirmed, multi-point observation of an extrasolar object from an extrasolar vantage point. Science Daily and other public-facing portals translated this dry technical triumph into a narrative of human achievement, highlighting how this Martian perspective provided a new, independent baseline for measurement. For the first time, humanity was triangulating the path of an interstellar traveler, not from one planet, but from two. This was the birth of a true interplanetary observatory network. But does a more precise measurement of its path merely tell us where it is going, or could it begin to hint at where it has been, and what forces shaped its epic journey? The first and most immediate level of analysis is one of pure celestial mechanics. With observational data points separated by hundreds of millions of kilometers, the orbital path of 3I Atlas could be refined to an unprecedented degree. Its speed, its inclination, its precise trajectory out of our solar system, all these parameters were suddenly known with a new order of certainty. According to current models, this level of precision allows us to run more accurate simulations of its past, tracing its path backwards through the galaxy to potentially identify its parent star system. It is a triumph of positional astronomy, a direct application of the same principles used to track asteroids and comets of local origin, but on a galactic scale. Yet, if this object is merely a passive piece of cosmic debris, a simple rock ejected by some ancient gravitational upheaval, why would such a precise measurement feel like we are only reading the first line of a much deeper story? This leads us to the second level of analysis, where the data from Mars presents its first true anomaly. Independent of the terrestrial observatories, the instruments in Martian orbit detected subtle, rapid fluctuations in the object's brightness. These were not the slow, predictable changes caused by rotation, but sharper, more spontaneous flickers. The mainstream scientific explanation suggests this could be due to outgassing pockets of volatile ices trapped deep within the visitor's nucleus, suddenly sublimating into gas when heated by the sun. jetting dust and debris into space and temporarily increasing its reflectivity. This is a well-documented behavior for comets within our own solar system. However, the pattern of these Martian-observed fluctuations did not perfectly correlate with the object's solar proximity or its rotational phase, defying straightforward cometry models. But what if this outgassing is not a simple natural process? What if the flickering light is not the random venting of ancient ices, but the signature of a more structured, perhaps even a more deliberate, release? It is at the third and most profound level of analysis that the event of October 12th transcends mere observation and enters the realm of the deeply speculative. The MAVEN orbiter, designed to study the Martian atmosphere's interaction with the solar wind, also carries a sophisticated radio spectrometer. As the cold firework of 3I Atlas's tail illuminated the Martian sky, MAVEN detected a transient, non-repeating signal in the radio band. It was a faint, complex pulse, a whisper in the static. Almost simultaneously, a dedicated 21-centimeter hydrogen line radio telescope on Earth, tasked with monitoring the object, registered an echo of that same signal. The two detections, separated by interplanetary space, formed a brief, perfect duet. Scientists suggest this could be a remarkable coincidence, a pair of instrumental glitches, or a fleeting burst of cosmic interference, perfectly aligned in time. The known laws of physics provide no mechanism for a simple cometary body to generate such a coordinated, wideband emission. The conservative view holds that we are witnessing a new, unknown type of natural plasma emission, perhaps triggered by the object's interaction with the different magnetic and solar wind environments near Earth and Mars. Yet, the synchronicity is haunting. Could the vast, silent distances between worlds have become a medium for a form of communication we are only just beginning to perceive? The implications of this interplanetary duet are as far-reaching as they are unsettling. It suggests that the study of interstellar objects can no longer be confined to a single viewpoint. The era of the solitary earthbound observer is over, replaced by the necessity of a multi-station, interplanetary listening network. Mars, with its thin atmosphere and lack of radio pollution, provides an ideal second ear. Future missions to the moons of Jupiter or the cloud tops of Venus could add more voices to this chorus. This becomes the new standard, a distributed sensor net cast into the solar system, designed not just to see, but to listen. It is a logical progression of our scientific reach. The way to filter out local noise and isolate the true signal from the depths of the galaxy. But if we are building a network to listen, what profound responsibility do we bear for what we might one day hear? This shift in perspective, from a single world to a system-wide observatory, forces a fundamental recalibration of our place in the cosmos. When only Earth saw an interstellar visitor, it was a spectacle for humanity. When Mars also sees it, and when the space between them carries a whisper, it becomes a dialogue for the solar system. We are no longer just inhabitants of a planet looking out. We are a civilization beginning to use its entire celestial neighborhood as an instrument. The very definition of a baseline has expanded from a few thousand kilometers on Earth's surface to hundreds of millions of kilometers across interplanetary space. This new baseline allows us to calculate everything anew: the trajectory, the nature, and perhaps even the intent of these silent travelers from the abyss. But in recalculating their paths and their properties, might we also be forced to recalculate the probability of our own solitude? The scientific process, however, is not conducted in a vacuum of pure data. It is framed and interpreted through the lens of public discourse and media narrative, a realm where consensus is built and dissenting voices are amplified or silenced. How will a world, just beginning to grasp the implications of a silent sky on two planets, process the official story?